Hello everyone, welcome to Synthesis Workshop. Today we are joined by Johannes Lamhauge. Johannes obtained his PhD in the Jorgensen lab in 2023, where he worked on developing enamine-enabled asymmetric organocatalytic Umpa-Long reactions towards 1,3-dipolar cycloadditions. After a research exchange at the Technical University of Munich, where he focused on developing flavin-based organophotocatalysts in the Storch lab, he teamed up again with the Jorgensen lab and completed postdoctoral research here. He currently works as a medicinal chemist at Lundbeck in Copenhagen, Denmark, where he's engaged in drug discovery for new medicines to treat central nervous system diseases. And with that, I'll let you get started. Thank you very much for joining us today.
Thank you for inviting me on to the Synthesis Workshop. I'm excited to share to you today some of the work we do in the Jorgensen Research Group. Specifically, I'll present to you today a recent publication we had in Chem European Journal on how we developed an organocatalyzed 1,3-dipolar cycloaddition to enantioselectively construct functionalized tropane scaffolds. Tropane alkaloids define a large family of natural products, which are recognized by a common structural motif, an 8-atabicyclo 3-to-1-octane core. They occur as secondary metabolites among multiple plant species, such as the coca, nightshade, mulberry, and bindweed families, and the biological effects associated with tropane alkaloids have been known for millennia. The most infamous examples within this class of compounds is probably cocaine and atropine. With well-documented and diverse biological effects associated with tropane alkaloids, it is of course not surprising that various pharmaceutical candidates have been developed around the bicyclic tropane scaffold. Now, an interesting thing to note is that although the bicyclic core itself is achiral, the biologically relevant tropane alkaloids are often asymmetrically substituted. This fact necessitates the development of asymmetric methodologies to enable the synthesis of optically active tropane analogues. Traditionally, the most common ways to achieve this is based on functionalizations around a pre-existing bicyclic scaffold. Typically, these methodologies rely on kinetic or dynamic kinetic resolutions of tropanoid compounds or desymmetrization reactions based around tropinone. However, there's also a different approach. One could envision that any eventual stereocenters could be set concurrently with formation of the bicyclic structure itself. If we evaluate the structure, one such approach could be a 5+2 cycloaddition reaction. This disconnection gives us an olefin together with a cyclic nitrogenous 1,3-dipole. This type of chemistry is not new. It was first reported by Katritzky in 1970. He was able to show that these 3-oxidopyridinium betanes were suitable 1,3-dipoles, which would react with activated olefins to deliver the bicyclic tropane scaffold. Now, these 3-oxidopyridinium betanes are very interesting reagents. They are derived from the quaternary salts of 3-hydroxypyridine, which upon deprotonation forms a zwitterionic species in which the charges cannot be neutralized by any resonance form. This phenomenon is also known as a mesoionic compound. They are very easy to prepare, and they show an extremely diverse set of reactivity patterns. For instance, as we saw just before, when given a 2-pi component, it reacts over the pyridine 2 and 6 positions in a 5+2 cycloaddition. However, when given a 4-pi component, it reacts over the pyridine 2 and 4 positions in a 5+4 cycloaddition. What's further is that when given a 2-pi component that's geometrically different than an olefin, for instance a ketene, it can react over the pyridine 2 position and the oxygen atom in a 3+2 cycloaddition. It's also worthwhile to note that if you evaluate the electron count of all of these cycloaddition patterns, they are all thermally allowed by the Woodward-Hoffman rules. But as synthetic chemists, we of course want to be able to select which cycloaddition reactivity that's operating, and to us, that's the 5+2 cycloaddition. If we review the literature on asymmetric 5+2 cycloadditions, we find that all previous examples have been employing chiral auxiliaries, either tethered to the nitrogen atom on the pyridine ring or tethered to the olefin. A common theme for these previously reported methodologies is a set of very interesting selectivity challenges. They often deliver mixtures of both endo and exo products or a mixture of regioisomers. Now, this set up our motivation to develop a catalytic variant of pyridinium betane cycloadditions that can offer a higher degree of selectivity. So how do we see to achieve this? Well, the research in our group emphasizes on aminocatalysis, and employing this to develop novel activation modes and new reactions using this type of organocatalyst. So before continuing, I'll just go through some of the main themes behind asymmetric aminocatalysis. It can be divided into two principal activation modes, both of which employ small, optically active amines as catalysts. On one side we have enamine catalysis. Here an enolysable aldehyde or ketone condenses with the aminocatalyst to form an intermediary iminium ion. This can deprotonate to form an enamine, which is the reactive intermediate. The chiral information on the aminocatalyst can then dictate to which side the enamine attacks an electrophile, in turn setting a stereocenter and releasing an enantiomer-enriched product upon hydrolysis. In this way, enamine catalysis can be used for enantioselective alpha functionalization reactions. On the other side we have iminium ion catalysis. Here an enal condenses with the aminocatalyst to form the reactive iminium ion intermediate. This is activated in the beta position for a Michael type addition, and as before, the chiral information on the aminocatalyst can dictate to which side the addition occurs. And upon hydrolysis we release a beta functionalized product. Now a conceptual merger between the two activation modes of enamine catalysis and iminium ion catalysis is a third activation mode known as dienamine catalysis. Here an enal is also employed, but in this case with a remote enolysable position. Upon condensation with an aminocatalyst, we get a dienamine species which is activated in the gamma position to react with an electrophile. And doing this we reveal an iminium ion which, as we know, is activated in the beta or ipsi position for nucleophilic attack. This substrate design allows for multiple stereoselective functionalization reactions to be promoted by the aminocatalyst. But this activation mode also gives access to an extended activated pi system which is well suited for cycloaddition reactions. So if we then return to our analysis of tropane synthesis by a 5+2 cycloaddition, we can recognize that the 1,3 dipole can be derived from a 3-oxidopyridinium betaine, and the olefin can be derived from a dienamine. So how do we go about achieving this? Our model reaction is based on using croton aldehyde as a precursor for the dienamine species, as well as a 3-oxidopyridinium betaine. For this reaction we also want to use a prototypical type of aminocatalyst. In this case we use a diaryl prolinol silyl ether type catalyst, which is also commonly known as the Janssen-Hayashi type catalyst. For the choice of 1,3 dipole we also recognize that we need an electrophilic 1,3 dipole, since we match it up with an electron-rich dienamine. It's known from the literature that pyridinium betaines equipped with an electron withdrawing group on the nitrogen atom offer such dipole. We identified this dimethylpyrimidine unit as a suitable activating group. Inspired by the previous examples of such 5+2 cycloadditions, for this reaction we should expect endo and exo isomers as well as regio isomers. But there are actually two different ways we can perform this reaction. The 3-oxidopyridinium betaine cannot be isolated in this case, so it has to be made in situ. One way to do this is to take the pyridinium salt and treat it with a base to liberate the free oxidopyridinium betaine. However, what happens when you do this is that the free betaine immediately dimerizes to form a regioisomeric mixture of dimers. But this dimerization is reversible, and since the dimer is an easily isolable solid, we might as well consider both the HCl salt and the dimer as viable precursors for the free betaine. This gives us an interesting choice of either using an acidic precursor, which is the HCl salt, or a basic precursor, which is the dimer. Now contrasting the two methods, we see that using the HCl salt together with triethylamine as a base, we get 65% of a cycloadduct. This is the endo product as the major product in a 1.4:1 endo-exo ratio and a greater than 20:1 regioisomeric ratio. Gratifyingly, we also see that we get the product in 35% EE. However, if we use the dimer as the source of the betaine and omitting the triethylamine base, we get the cycloadduct in 41% yield, still fairly unselective with regards to endo-exo as a 1.2:1 ratio, a greater than 20:1 regioisomeric ratio, but a substantial increase in enantioselectivity to 82% EE. Jumping forward to the optimized reaction conditions, we were able to utilize that we had our reagent in two different forms, an acidic form and a basic form. and varying the ratio between the betaine precursors, we were able to tune in the most selective reaction conditions using the dimer and the HCl salt in a 9:1 mixture. For the choice of catalyst, we found that increasing the steric bulk of the silyl ether moiety tethered to the catalyst was beneficial, as well as using diphenyl phosphate as a co-catalyst. Under these conditions, we generally see the endo-cycloadduct as the major product, as well as a small amount of a regioisomer. And on this, we were able to establish a substrate scope. Our model reaction using croton aldehyde delivered the endo-cycloadduct in quantitative yield and 97% EE, with a greater than 20:1 exo to endo ratio and a 16:1 regioisomeric ratio. Varying the substituents at different positions around the aldehyde substrate was well tolerated, giving generally lower yields but maintaining a high degree of enantioselectivity, endo-exoselectivity, and regioselectivity. But here there are two entries that I would like to highlight, because two aldehydes behaved very differently in the reaction compared to the others. The one to the left exclusively gave the endo-regioisomer as the sole cycloaddition product, while the one to the right gave exclusively the exoisomer and not the endoisomer as we saw in all other cases. I want you to keep these two entries in mind for later when we come back to the reason for this. The scope of pyridinium betaines was somewhat more limited than the scope of aldehydes. We were able to effectively modify the N-pyrimidine substituent while maintaining similar levels of yield and selectivity. However, introducing substituents around the pyridine ring itself challenged our optimized reaction conditions, since these betaines did not undergo dimerization. Luckily, we could revert back to the reaction conditions employing the HCl salt together with an external base to generate the betaine. This delivered our desired cycloadducts in a lower level of selectivity compared to the dimer approach. To this, we must conclude that our ability to selectively introduce various substituents on this right side of the molecule is limited. But this side of the molecule also has an enone embedded into the bicyclic scaffold, which is an excellent handle for chemical modification. This encouraged us to embark on a campaign of synthetic elaborations to further diversify the set of available tropane scaffolds. First, we performed the scale-up reaction to provide material for these studies. The scale-up performed almost identically to the small-scale reaction. From this cycloadduct, a selective reduction of the aldehyde was performed to give us a starting point for structural diversification. We were able to perform a conjugate addition with a methyl cuprate, loose reduction and Grignard addition to the ketone, as well as a Diels-Alder reaction, all in good yields and perfect diastereoselectivity. We were also able to perform an intramolecular oxamical addition of the primary alcohol to the enone system by treating the compound with sodium methoxide and methanol. This cyclid ether was used as a starting point for an alpha functionalization with prenyl bromide, and also reduction and following esterification gave us a single crystal, which allowed us to assign the absolute configuration by X-ray diffraction. Finally, we were also able to demonstrate that the pyrimidine activating group could be cleaved by acidic hydrolysis, treating it with concentrated hydrochloric acid. The next thing we decided to investigate was some more fundamental questions about the reaction mechanism. Through the studies, we have observed three different cycloadducts in the reaction mixture. There's the endo product, which is the major cycloadduct, but then there's also the corresponding exo product. And finally, we also, in some cases, observe the regioisomer. All three products must arise from some perturbations of similar 5+2 cycloadditions. But I also started this talk by saying that 3-oxidopyridinium betaines can undergo various different cycloadditions. With a dienamine, we can envision both a 5+4 and a 3+2 cycloaddition pathway. The question then remains what actually governs our overall selectivity, both in terms of the different 5+2 pathways, but also between different periisomers such as the 5+4 and the 3+2 pathways. To investigate this question, we resorted to modeling the reaction by DFT calculations. We started out by examining the initial approach of a dienamine to the 3-oxidopyridinium betaine. Here we identified 4 relevant transition states. The leftmost transition states correspond to the 2 enantiomers of the observed major endo product. The middle transition state leads to the exo product, while the rightmost transition state corresponds to a regioisomeric pathway. An interesting thing to note here is that all transition states point to a stepwise cycloaddition mechanism, with the exception of the regioisomeric pathway, which is concerted. We also see that the lowest energy transition state indeed is the one leading to the major enantiomer of the endo product that we do in fact experimentally observe. This is also the only transition state in which the dienamine geometry is oriented in an S-cis conformation, whereas in all other transition states the dienamine is S-trans. To rationalize this geometric preference, we performed the distortion interaction activation analysis as developed by Bickeltaub and Haug. This allows us to deconvolute the various contributions from positive interactions between the reacting species from the energy penalty of strain in the transition state. Here we find that an S-cis conformation positively aligns partial charges in the reacting species, which offset the energy cost of adopting an S-cis conformation. We were also able to qualitatively verify this interaction by analysis of NCI plots. In summary, the selectivity between the various 5+2 cycloadducts is governed by dienamine geometry. So what about the selectivity to a 5+2 cycloaddition over other cycloadditions? To answer this, we have to evaluate the formation of the second bond in the stepwise cycloaddition. This is the intermediate after the initial bond formation. The only difference between the various cycloaddition pathways is where this iminium ion hovering above the pyridine ring closes down for the second bond. To make a 5+2 cycloadduct, we have to follow the green line, which in the intermediate comes with a distance of 3.13 angstrom. To close down to a 5+4 adduct, we have to follow the blue line, which in this case comes with an even closer distance of 2.70 angstrom. And finally, a 3+2 cycloaddition would require rotation of the iminium ion over to the oxygen atom. Now looking at the transition states for the second bond, we find that the lowest energy transition state is one leading to the 5+4 cycloadduct. Now this is surprising because the 5+4 cycloadduct we don't observe in the reaction. But we can also recognize that we cannot liberate the catalyst from a 5+4 cycloadduct by hydrolysis. Neither is there a good way to do it by elimination, so basically in this structure the catalyst is trapped. The barrier for reversal is fairly low, and instead the intermediate can follow through the green line, which leads to the 5+2 cycloadduct, which is also the thermodynamic product. For completion, we also modeled the formation of a 3+2 cycloadduct, which was higher in energy compared to the other transition states, and the cycloadduct is also endergonic compared to the starting materials. So we can summarize our conclusions in the catalytic cycle. First, our aminocatalyst condenses with our enal to form a dienamine. This prefers an S-trans conformation but can rotate into an S-cis conformation. We found that minor isomers were derived from reactions through the S-trans conformations, whereas our major isomer is through the S-cis conformation. After the first bond formation with the dipole, the intermediate kinetically prefers to form an off-cycle 5+4 cycloadduct. But the dynamic system reverts back to the intermediate, which then follows the thermodynamic pathway to form the desired 5+2 cycloadduct. The tropane product is liberated by hydrolysis, completing the catalytic cycle. And now I want to bring you back to the two entries from the substrate scope which behave differently. They derive from the two aldehydes you see to the left. The thing they have in common is that the dienamine derived from both aldehydes are either unable or unlikely to react through an S-cis conformation. Thereby it makes sense that for these reactions we observe different isomers. So in summary, we have developed an enantioselective synthesis of tropane scaffolds by a 5+2 cycloaddition between catalytic dienamines and 3-oxidopyridinium betaines. The methodology provides access to diversely functionalized optically active tropanes with ample opportunity for further synthetic modifications. The high level of selectivity between enantiomers, endo-exoisomers and regioisomers is governed by strict selection of enamine geometry, and paraselectivity is derived from dynamic interconversion between cycloadducts, eventually favoring a 5+2 cycloaddition. And here at the end I of course have to thank the people that made this work possible. I'll thank my amazing co-authors, I'd also like to thank Professor Carl Anker Jørgensen and the entire Jørgensen group, and our funding bodies. And finally, I would also like to thank the Synthesis Workshop for giving me the opportunity to share the work from the Carl Anker Jørgensen group. And thank you all for your attention.
Thank you for tuning into this Research Spotlight episode, and thank you, Johannes, for sharing your very interesting research with us. If you enjoyed the episode, you can support us by subscribing and telling your peers about this podcast. And feel free to send us any questions or comments that you have. Follow us on Twitter to stay up to date, and see you all next time.